Hello, my name is Raul Cornejo, and this is LabActivity number 6 video for class EEE3303 Lab. First, circuit just had to get this transistor in the active region. So the bias was for the collector was 5 volts DC, base resistor was 10 kilo ohms, and the low resistor was 1 kilo ohm. The measured value collector emitter junction voltage was 0.8 volts. Base emitter voltage was 0.7 volts. Base collector voltage was a negative 1.29 millivolts. And the measurements show that this resistor is in the active region. Collector base junction is reverse bias, while the emitter base junction is forward bias. And you can see that we got similar results from the multisim. And here's the circuit itself. For part 2, the collector bias was 2 volts DC, whereas the input AC was a 0.25 BM, or basically 0.50 volts peak to peak AC. Base resistor was 1 kilo ohm, the lower resistor was 10 kilo ohm. And here omega is just left with omega because the frequency needed to be changed in order to observe the coupling capacitors, how the coupling capacitor affected the circuit. And it's expected that the coupling capacitor should not allow gain of very low frequencies, or just basically is attenuating the low frequencies. Well, 100 hertz, we got voltage input 500.37 millivolts peak to peak, voltage output 125.71 millivolts. The gain was measured to be a 0.39. So my results. And here is the multisim simulation. A very similar result. Yeah, and here's a 500 hertz input frequency. We got the voltage input of 100.17 millivolts, voltage output 587.25 millivolts peak to peak. So there's a slight gain in this one, a 1.17. Here is the signal input to output. Similar results in the multisim, input, output. Alright, 1 kilohertz input frequency, we got a voltage input of 100.25 millivolts peak to peak, voltage output 618.09 millivolts peak to peak, and the gain is measured to be 1.24. Right there. Yeah. And finally, the 5 kilohertz input frequency, we get voltage input 497.36 millivolts peak to peak. Voltage output 622.81 millivolts peak to peak. Voltage gain is 1.25. So the maximum gain is shown to be around 1.25. Very low frequency signals are attenuated and not amplified by the transistor due to the coupling capacitor that precedes it. So it's around 100 and 200 hertz that the signals actually begin to be allowed to pass, but receive very little amplification, and above 1 kilohertz the signals are amplified with a gain of 1.25. And here is the circuit itself. Here's the coupling capacitor. Here's the transistor. This is the input AC, input DC. So, okay, for part 3 was to set up a Darlington configuration circuit. So for this one, PCC was 3 volts, base resistor was 10 kilo ohms, low resistor was 1 kilo ohm. The current measure at the collector of the second transistor was 1.82 milliamps. The base current of the first transistor is 0.2 microamps. So it made us came out to be a very large value, 9100, due to the big change from this very small value to much bigger value compared to that. The regular beta of 2N3904 transistor, which are used for all the experiments, is around 100 to 300. But in here, the beta output is, because the output of the Darlington configuration is 9100, which is very high compared to the regular input. And here is the circuit. Here's the first transistor. There's a second transistor, and they are both connected right there. And I actually had to use a different multimeter to measure the small current base value of the first transistor. Is my You can see it actually had it set to 200 microamps, just so I could measure the small to super small value. And similar results are also found in the multi-sim, where the transistor collector output is 1.754 milliamps, and the base current of the first transistor is 179 nanoamps, a very small value. And you can see the multi-sim simulations do closely match the measure results, so it's a way to indicate that the actual circuits are behaving as expected. And thank you for watching.